Okay, let's take a look at section 1.6, graphs of functions. We've already looked at a few graphs, and what's written in this section was kind of implied for the rest of this. We've drawn pictures already of parabolas. We've drawn pictures of arrays. We've drawn um, different regions in the plane. But now we're going to formalize this stuff. So uh, let's go for it. Uh, the fundamental graphing principle for functions here. So all this is saying is that a point is on the graph only when that y value is the function value that we put in when we get, y is the function value we get when we use x as an input. So, yeah, we can, what's sort of implied here is that we can generate ourselves a whole bunch of points just by picking out values for x and finding corresponding function values, right? And this is what we did previously when we were drawing graphs, but we called this thing y, right? So we're just going to do the same thing. So for this guy here, what we'll probably end up wanting to do is just, pick your buddies, -1, 0, 1, and we'll see what happens. So if we put in 1 into this function, we're going to get, or excuse me, -1. We just put -1 wherever we see the number, the variable x in the function, and we can carry this operation out, right? 1 minus 2 is -1, minus 3 would be -4. We can do, for 0, we got 0 squared plus 2 times 0 minus 3, so that's -3. We put a 1 in there, we got 1 squared plus 2 times 1 minus 3, so we got 1 plus 2 is 3, minus 3 would give us 0. And now we can start, putting the points on the graph, right? So our points x comma f of x, we can list them, right? -1, -4, we've got 0, -3, we've got 1, 0, and we can put those on the graph. Boop, boop, boop. And then if we want to make a better picture, we ought to put more points on there, right? So maybe I'll put a 2 on there, and maybe we'll put -2. See where that is. So if we do 2, we got 2 squared plus 2 times 2 minus 3. So that's 4 plus 4 is 8, minus 3 would be 5. So we got 2, 5 on there. It goes up pretty quick. And then -2, we got -2 squared plus 2 times -2 minus 3. And we can do this. So we got 4 minus 4 minus 3. So 4 minus 4 would be 0, minus 3 would be minus 3. So we got the point -2, -3, and we can plot that point, -2, -3. So this is going to look like that familiar parabola shape, right? So we're going to take, when we draw this on WebAssign, we're going to click on this little parabola tool that we've already used. The first point you click needs to be the vertex, which is this point. We'll give that a better treatment for what we mean by a vertex later in another section. But we want that point right there, and then click any other point on the parabola, and it'll populate that graph for you. But the big idea is that we need to plot enough points that we start seeing a pattern, and then we just connect the dots. Okay, great. Yeah, we did one of these in the previous section. Let's do another one where we're going to graph a piecewise defined function. So maybe let's have piecewise defined. So let's say it looks like square root of x minus 4 when or I guess they use if, don't they? So let me put that as a future piece. So let's have x squared if x less than or equal to 0, and let's have square root of x if x is bigger than 1. Okay, so we want to draw a piecewise defined function. So as we looked at last section, or one of the previous sections, Piecewise defined functions, here's our domain. So our domain is the set of all numbers that are less than or equal to 0, so negative infinity to 0, and all the numbers that are bigger than 1, right? So maybe we can make a note that the function is not defined on the interval 0 to 1. Right, so there are no function values whose ordered pairs have a y-coordinate, have an x-coordinate between 0 and 1. Okay, so, well, let's take a look. So our function here, as we've said before, is defined in pieces, right? So we have, one piece and another piece. We got two pieces here. So our graph is going to look like the graph of this, and this is a really familiar one, right? We can rattle off a bunch of points on here, 0, 0, 1, 1, negative 1, 1, and then we can draw this graph. We know what it looks like. We're familiar with it. And we can also draw this one, right? And maybe we need to put some ordered pairs in there. We can make a statement about the domain here, right? It's radical. So we need this thing to be bigger than or equal to 0. So if we want to, we can rattle off some points here. Great. So we put 0 in there, square root of 0, this is 0, square root of 1, this is 1, square root of 2 is, well, that's simplified. Square root of 3, that's also simplified. Square root of 4, this is 2. So if we wanted to write our ordered pairs, we've got f of x being paired together. We got 0, 0, we got 1, 1, we've got 2, square root of 2, 2, square root of 3, and we got 4, 2. That one should be a 3. Excuse me. All right, so the points we want to graph are this one, this one, this one, right? Because these guys are somehow harder to draw because they're not whole numbers, right? So let's just draw this. We've got y equals square root of x. I want these ordered pairs on there, 0, 0, 1, 1, 2, 3, 4, 4, 2. Whoop. And if we really wanted to, we could put some more points on here and draw a better picture. Or we could put those guys on there, right? Give us a little better idea where the graph goes. Okay, so we know that a piecewise function is defined in pieces. So this one here has two distinct pieces. Well, the piece, this one looks like this guy. This one looks like this guy. And now we just have to say, make a distinction of these domain regions, right? So this is only going to look like this square function when we are in this domain region, right? So where we're less than or equal to 0. So it's here and on. So only there. And now for this one here, we're only looking at this one where x is bigger than 1. So this is from 1 to infinity. So I'm only going to consider here and on. And we're going to use an open dot here, right? Because the function is not defined at x equal 1. So for our piecewise defined function here, we're going to just put the pictures together. So I've got my branch that goes off to the left here. This piece looks like a parabola. And then our other piece that looks like a radical function is here. And this would go like that. Okay, so here is our nice graph of the piecewise defined function. Now, we ought to be thinking of it in our heads as, two pieces here, but we're not including what domain region we don't want, right? So all of these are gone. And we're just looking at the green parts and, put those together. There's our beautiful graph. Okay, great. We got another definition here. The zeros of a function are the solutions to the equation f of x equals 0. So yeah, that means that x is a zero of a function f. If and only if we get 0 as an output when we put in that number. So find the zeros of this function here. So we could make ourselves a little chart, and we could rattle through a bunch of x values, and then we find 0, and hey, there it is. But that's going to be such a big pain for you to do. Rather, we should just solve that equation, right? So we want to solve f of x equal 0. So this one, we're just going to put in, hey, there's the function, right? X squared minus 4x plus 1 equals 0. And this is what we need to solve now. Okay, so we can do that. If we've got a quadratic function here, we have a couple different methods that we want to use. We would first try to factor this, but we know that there are no two factors of 1 that are going to add to be 4, so that's not going to work out for us. So we're going to need to use that quadratic formula. So we recall that if we have anything of this form, then we can immediately spit out the solution. This ought to be something that we recall from previous coursework, the quadratic formula. We're going to use this a lot. So we can solve this quadratic equation, right? We have A is 1, B is -4, C is 1, right? And we're just, again, looking at the coefficients here. Coefficient there's a 1, right? So A is that number, B is that number, C is this number. We're just matching it up, A, B, C, right? And now we can take these and plop them into the nice formula guy. So negative b would be -4 plus or minus the square root of b squared, so -4 squared, minus 4 times a times c, those are both 1, divide by 2 times a, which is 1. And now we play the simplification game. So I got 4 out front, plus or minus the square root of, what is this, 16 minus 4 would be 12 over 2. And we can continue on the simplification route. We know that 12, square root of 12 is 2 square roots of 3, right? Because 12 is 4 times 3, divided by 2. And then we're done. We cancel out all of our common factors. We got 2 plus minus square root 3. So in this case, we would say the zeros of f of x are x equal 2 plus square root of 3 and 2 minus square root of 3. We got 2 of them, right? Maybe put this in a little box. Now, what we're saying here is also true the other way around, right? So if I put this, so just to be specific about what I just said, we can phrase this in this sentence right here and say the zeros of f of x are this. Similarly, we could also say f of, whoops, I don't want to be moving here, f of 2 plus square root of 3 equals 0. And f of 2 minus square root of 3 equals 0. All right, these two statements are saying the same thing. And we're going to use that fact later. So when we say find the zeros of a function, it's the same as asking what inputs are going to give you 0 as a result, or a function value. Okay, so now we're going to talk about symmetry. So symmetry, none of this stuff is going to be different than what we talked about before. We've already talked about symmetry, and let's maybe draw a picture down here. So I want to talk about a point xy. But now we're not talking about xy. We're talking about x comma f of x, right? Because now we're injecting this into our conversation, the new definition here. So if I have a function and it has that point right there on it, if I've got y-axis symmetry, I'm also going to have a point over here, right? And maybe I'll put that in a different color here. So if I've got y-axis symmetry, then that point right here is going to need to be there, right? So they're going to have the same y coordinate, right? It's going to be f of x, but the x coordinate is going to be different, right? Negative x comma f of x, right? Well, these two are the same as, right? Those two guys are the same because this is the general notation, right? Whenever I have an x value, the y coordinate that goes with it is just the function with that value that goes through, right? So in particular, we need this to be equal to this, right? If two ordered pairs are the same, we need these guys to be the same, right? The x coordinates have to be the same and the y coordinates can be the same, have to be the same. So that's the way we're going to be checking to see if we have symmetry, is we can run a negative x through there and we get the same value back. All right, so let's do the same thing with the origin symmetry. If I've got origin symmetry and I've got this point on there, that means that the point down here has to be present. Well, that's going to have a negative x coordinate, and we're going to have f, if I put that negative x coordinate in there, well, thinking about what this is, that's f of x, right? And now down on the y-axis down here, that's a reflection of this, right? So negative of what we have up here is reflected down as a negative of that y value. Well, that means that these guys have to be the same, right? So that means that this one has to be the same as this one. So if we put a negative x in through our function, we're going to get the negative version of what we would put in if I had the positive number in there. So putting that in a nice little package up here, a graph of a function f is symmetric about the origin if and only if I put a negative x in there and I get the negative version of that function back, right? So this is the same. We're talking about the same thing. We're talking about symmetry in the idea is the same as we've had in previous sections, but we're just using the function notation now. Something that the maybe more savvy of us are probably notice is that we only have two types of symmetry here. Well, think about this for a second. If we had the third symmetry, which is x-axis symmetry, what other point would have to be on there? If I've got this guy right here, and x-axis symmetry would have to be down here, right? Well, what's wrong with that? If this point is on there, we've got the same y value, right? So these two things here, 2 points, they're on the same vertical line. So we can conclude from this that no function has x-axis symmetry. Because if that's true, then we're going to have 2 points that lie on a vertical line, and we talked about this in the last section or two, that vertical line test, right? So this can't happen. All right, so now we're going to go for it. So we want to know if these functions here are symmetric about the x-axis, y-axis, or the origin. Well, we just got done saying it can't be symmetric about the x-axis. So let's go for it. To do any of these, we're going to consider what happens when I put a negative in there. So put a negative in there. So f here, we're going to put 2 over 5 plus and a negative number in there. All right, now we simplify it. We've got 2 in the numerator, 5 plus, what's this guy? We square negative x, we're going to get x squared, right? Well, we look and then compare that to our original function. Well, it's the same, right? So now for this first one, we say that this is symmetric about the y-axis, right? Because this statement here is true. I put in a negative x, and we found that that's equal to what we started with the original function, right? So we would say that this is even because f of negative x is the same as f of x. All right, great. And this is the same the same thing, the same process. We're going to do this for all of these functions. When we're checking to verify, is it odd, even, or neither, we're just going to do the same thing. Just put a negative number in there and see what happens. So let's do that for part 2 here. So for part 2, we got g of negative x. We can put that in there. So we got 2 and then negative x on top. 5 plus negative x squared on the bottom. And then we simplify it. So I've got negative number in the numerator, 5 plus, we square that, it becomes positive. Well, I can write a fraction. If I've got any fraction at all, I can put a negative out front, or I can put it out front of the numerator. I can put it out front of the middle of the bar, or I could put it out front of the denominator. It doesn't really matter. But we can write this. I mean, maybe this is a step extra that we don't exactly need to write. But this is just the negative version of what we started with, right? So we would say that this function is odd because when I ran a negative input through there, I ended up getting the negative version of what we started with. Okay, so great. We just put a negative x in for x, and we simplify it, and we say, is it the same or is it not the same? And if it's the same, well, we have that it's even. If it's not the same, we say either that it's got origin symmetry and it's odd, or like in this case here, we're going to say that it's neither even nor odd, right? So let's see why. So if I put a negative x in there for x, we got 2 times negative x, 5 negative x plus negative x to the third. Okay, so simplifying this guy, we multiply that through, we got negative 2x. We can say that we can have negative 5x there, and then cube a negative, it stays negative. So we might get to this point and say, hey, wait a minute. That's not the same as what I started with, and it doesn't really look like the negative version of what I started with. So we might be tempted to just say that it's neither one, but be careful with ones like these because we can see that those guys share a common factor, don't they? If we pulled a negative out of the numerator and a negative out of the denominator, it would look like this. And then that negative cancels out, doesn't it? We got 2x over 5x plus x cubed. Well, hey, compare that to what we started with, and it's the same, right? So this is what we started with. And we would say that this is even because h of negative x is the same as h of x. Okay, great. So we didn't have one that was neither, I guess. So let's maybe we can manufacture one that's going to come up with neither symmetry. So how about let's add one here. Let's say k of x is square root of x minus 5. All right, well, to test this, we're going to put in a negative x. So we got square root of negative x minus 5. So we've got square root of, well, we can drop the parentheses if we want to, negative x minus 5. And now at this point, we want to try to rearrange this so it's what we started with. Well, even if we factored that x, or negative out, we would have x plus 5. And that's different, right? So this is not what we started with. And it's also not the negative of what we started with. So we would say that it has neither symmetry. So it's neither even nor odd. Neither one, right? Because it's not the function we started with, and it's not the negative version of the thing we started with either. Real common error to make here is to plug in particular values for x. And if we did, like, put a negative 2 in there, or something, instead of the negative x, that's the common error, is to like put in negative 1, show that this one point is symmetric. And that's nice, and we can sure show that individual points are symmetric, but that doesn't show that the whole function is symmetric. So for example, if I did, let's use f here. So if I looked at this guy and I wanted to, your temptation, and let's give in to our temptation, and we want to say, what's f of 1? Well, I'm going to have 2 over 5 plus 1 squared, so that's 2 over 6, so 1/3. Okay, great. F of -1, what's that? So that's 2 over 5 plus -1 squared, so that's 2 over 6 is 1/3. So you're going to get to, at this point, and you're going to say, hey, those are the same, so that means it's got to be symmetric. Well, that's not true, right? All we've shown with this is that this point and this point are symmetric and present on the graph. That's all we've shown. We didn't say anything about any of the other points. Now, I know that some of us might know immediately what this graph looks like, and maybe that's true, maybe it's not. But we do have to consider that maybe this thing isn't symmetric. Maybe it's just got this pair is symmetric, and maybe the other parts go up here and we've got some goofiness going on in there, and it's not symmetric about anything. That could happen. So there is a distinction between finding symmetry in points versus finding symmetry with the whole function, right? If we're going to say that a function is symmetric about anything just by plotting points, we can't do that because we would have to exhibit infinitely many points for which this is true. We just want to do it in general, so we don't use actual numbers. We're just going to say, all right, put a negative version of our input in there and see what happens. If that didn't make sense, please don't be quiet about it. Let me know, and we can absolutely talk about this some more. Okay. So general function behavior. Okay, so we have an intuitive notion of what it means for something to increase, decrease, and be constant. We're just going to write mathy versions of what these behaviors mean. So we've got a function defined on some interval I. So let's think about this graphically. If I've got a function, maybe I can draw it just like this. That's fine. So we know, our mastery of the English language suggests that we know that what it means for something to increase, right? It goes up. The difficulty with just saying it goes up is that we don't really have an orientation here. So we need to say it goes up as I move a certain direction. So we want to say maybe it goes up as we go left to right. So pointing at this one, let me make an easier one here. So how about just a parabola? So maybe like this. And let's say that this is the point A, and this is the point B. So our function is defined on some interval I. Maybe we can just say, hey, this is the interval I. And we got 2 points in I. So we've got A and we've got B. And we're going to say that our function is increasing if and only if, well, we want our function values to go up. So we want f of A to be less than or equal to f of B. So something to the left of something else ought to be below that other thing, right? So let's draw a picture maybe a little better. So here, this is increasing. How wonderful. Here's A, here's B. This point right here and this point right here have y coordinates f of A and f of B, right? So we're increasing whenever some number is less than another one. Their function values also have to have that relationship. Same thing, we're going to say the same thing about decreasing, right? If we are decreasing and we're going down, then I'm going to have the point here, f of A, and the point here has f of B. So if we're decreasing as we move to the right, we're going to go down. So f of A has to be bigger than f of B. F of A has to be bigger than or equal to f of B. All right, great. And we say it's decreasing when this is true. And I bet we can guess what we're going to say when we're constant, right? So if it's constant, it's going to be the same value. So we've got f of b equal f of a, right? Oops. Okay, so we're just needing to orient ourselves by x values, right? So we got to refer to what we mean, increasing. What do you mean by increasing? Because if I looked at a graph that looked like this, and I say it's going up, well, it's going up on both sides. So which one do we mean? Or if I've got one that looks like this, I'd say it goes up. Well, what do you mean? It goes up over here. That's true, but it doesn't go up over here. So we have to be specific about what we're talking about, right? Okay, increasing, decreasing, and constant. So on graphs, that's not what we want just yet. So on graphs, let's draw a picture. And maybe we can have a relatively simple one here. Close dots. Oop. All right, so here's the function y equal f of x. And now we want to say, where is it? Increasing, decreasing, or constant. And we can do these, right? So where is it increasing? So I want to know all the intervals, so all the x intervals for which the graph goes up, right? So we're moving left to right, and we want to be increasing. So I want my function values to get bigger and bigger and bigger as we move through the interval. So, right, so we're looking for where the graph is going up from left to right. We're moving from left to right. Where does it go up? Well, right here, right? So we would just give that interval here. I think we define these as open intervals, right? On an interval I. Okay, so we should use open intervals for these, so use parentheses. So increasing here looks like from 0 to 1. Decreasing, we're going to do the same thing, right? We want all of the x intervals for which it's going down. So it goes down from, looks like 1, 2, 3, all the way to 3, 4, 5, 6, all the way to 6. We want to give an open interval. And then we say, where is it? Constant. Well, it's constant right in this interval. So we've got the interval from 1 to 3. And that's not doing what I want. There we go. Okay. And then we would put that open. Something that we usually make errors on is the fact that these are x-axis intervals. We use x values to describe locations on a graph. We should say usually. Right, we usually use x values to describe locations on a graph, mostly because that's why how we define functions, right? Any input is going to give you a unique output, so it makes more sense to talk about functions graphs in terms of their inputs, because there's exactly one output for each input. If we talked about it in terms of the y values, we might have repeats, like for example right here and right here. If I say look at the graph where y is equal to 1, that's not a very specific point, right? Because on this graph there are 2 points where y is equal to 1. But if I were to say look at the graph where x is equal to 2, there's only one point where x is equal to 2, right? So we're going to use x values to describe locations on a graph. All right, great. We did increasing, decreasing, and constant. These are pretty intuitive ideas, I think. Okay. So we got kind of a similar idea here. Suppose f is a function with f of a equal b. So we want to talk about what a local maximum is. So we have a local maximum at a point a, b, if and only if there's an open interval containing a, for which f of a is larger or equal to f of x for all x in I. So what this means is f of a is larger than all surrounding points. Right? It's larger than all the stuff around it. So if I have, here's a picture, here's a nice function, and we'd say, okay, here's the interval I, here's your interval I, and I've got my function value right here, here's A, this is the point AB, f of A equal B, right? So this is called a local maximum. Whenever I can take any value in this interval, like anything over here, anything in this interval, is going to give us a function value that is less than b here. So usually this is a pretty intuitive idea. We say local maximum if a point is higher up than all the other stuff around it, right? And this is kind of just a mathy way to write this. We say that f has a local minimum at a point AB if there's an open interval for which everything else around it is smaller, right? F of A is smaller. Maybe instead of smaller, we can say less than all the stuff around it. Right, so a picture of this might look like this, where here is our interval I. I've got my number A here, and that's the minimum. If I can take any value in here and run that through the function, it's going to give us a value that's bigger, right? Right, we got a local minimum here. Okay, wonderful. Okay, so these, right, the first two we had local minimum. So these others, maximum and minimum, sometimes we say absolute minimum or maximum. Sometimes we use that word, or we just omit any qualifiers at all. We just say it's the maximum, right? It's the biggest thing in the whole domain, or it's the smallest thing in the whole domain, right? So, for example, if I have a graph that looks like this, here's the point 2, it doesn't really matter, 2, 1, we would say that the minimum is f of 2, which is 1. So the minimum is 1 here. We refer to it as a function value, right? The minimum value is 1, and it's achieved at the function, or excuse me, at the x value 2. So good. Hopefully this is intuitive for us here. Okay, great. Let's maybe look at an example, and I can draw. So maybe this is AB. This is CD. And here's, now it's on a coordinate plane. That's great. So we can maybe list all of the stuff we just did. So this is the function y equal f of x. So we can say it's decreasing on which intervals here. So we want to know, where is it going down as I move left to right. So we're starting left, moving to the right, and we want to know, where is it going down? Well, wouldn't it be between these two x values? Decreasing on the interval AC. Is it decreasing anywhere else? Well, it looks like it's going up when we're less than A. Looks like it's going up when we're greater than C. So that's it for decreasing. Increasing. We want to say, where is it increasing? Well, it's increasing over here, right? As we move left to right, it's going up. So we would say negative infinity to A. And it's also increasing when we get past C here, right? So we would have union C to infinity. Okay, so increasing on two intervals there, decreasing on the one. We would say that it has a local max at x equal A. And we would say that the local max is f of a, which is b. Okay, we would have a local minimum where it's right here, right? The thing that's lower than the rest of the stuff around it. So we have a local minimum at x equals c, and we would say that the local minimum is f of c, which is d in this case. So we don't have any absolute max or min, right? Because our arrows mean it goes on and on forever up, and it goes on and on forever down. So there's no lowest value and there's no biggest value. Now, if I had a graph that looked, like this maybe, then it does have an absolute minimum, and it's right there, right? And it does have two local minimums, right? There's another one right there. So be careful, the distinction between absolute and local minimum and maximum. Okay, wonderful. So we can talk all about the graph of a function. So great. That's it. So thanks for watching the video. If you have any questions about anything at all, please let me know. Otherwise, have a great rest of your day.